Alright, page 7. Now we're actually going to use this to solve for differential equations. Alright, and basically the steps are you're going to do a Laplace transform to both sides of our differential equation. After you've done that, you're going to solve for cap y of s, the transformed equation. And then once you solve for y cap y of s, you're going to do the inverse transform, and you'll go back to t, and you've solved for the differential equation. Pretty cool, but also pretty long. So I'm going to show you the first example. And here we have the differential equation, y prime minus y equals 2 cosine 5t. And we're going to need this, y of 0 is equal to 0. Now, when we look to solving this, the first thing to do is apply the Laplace transform. And because it's because we're doing this because Laplace is linear, I can go ahead and apply it to each term. So the Laplace of y prime minus the Laplace of y is equal to 2 times the Laplace of cosine of 5t. Now, the Laplace of y prime is just like the Laplace of f, of f prime of t. So I'm going to go refer back to the last page and substitute in for the Laplace of y prime. It's just s cap y of s minus y of 0. So the Laplace of y prime is taken up by the first two terms. Minus the Laplace of y, well, the Laplace of just y is just, y cap y of s. And then Laplace of cosine of phi of t is going, since it's cosine, it's going to be s over s squared plus 5 squared, so 25 times 2. And I'm sorry, that's not 5, that's s. I think I said s. And it's very easy to get your s's and your 5's mixed up, so make sure that you know which is s, which is 5. Make sure you denote that as well. So we know what y of 0 is. It's 0, so that's 0. So I have sy of s minus y of s. And so I'm going to go ahead and combine these, and I'm going to get s minus 1 times cap y of s. And the reason why I wrote it this way is because I want y of s. I'm trying to solve for y of s, so I'm going to need that by itself. So that's why the s minus 1 is kind of pulled out, factored out. On the right-hand side, nothing's changed. 2s over s squared plus 25. Now to solve for y of s, I need to divide both sides by s minus 1. And when I do that, I get 2s times 1, which is 2s, s squared plus 25 times s minus 1. I'm going to write that as s squared minus 25 times s minus 1. And that should be plus. So make sure and denote that that's plus where it needs to be plus. All right. And so this is where partial fractions comes into play again. And so I have 2s over s squared plus 25 times s minus 1. That's going to be equal to, and then I'm just going to pull out the partial fractions. Because s squared plus 25 is one that's not going to be able to be factored. It needs to be over linear. So it's bs plus c over s squared plus 25. But I'm going to go ahead and pull that apart so I have 3 separate fractions. And now, in order to get rid of the denominator, 2s is going to equal to a times s squared plus 25. Then you multiply bs and c times s minus 1. So bs times s minus 1 plus c times s minus 1. Now, I'm going to go ahead and plug in my only 0 for s, which is 1, taken from s minus 1. When I plug that in, my b and c are going to both cancel out because they have an s minus 1 with them. That's why I didn't go ahead and multiply. So that b and c goes away, and I'm just left with a times s squared, which s is 1, so 1 squared, so 1 plus 25 is 26. S is 1, so 2 times s is 2. 2 equals a times 26. Divide both sides by 26. A equals 1/13. So I'm going to plug that in for a, and b and c are going to stay the same. Now I'm going to go ahead and distribute my b, c, and 1/13. So the first part is 1/13 s squared plus 2s over 13 plus bs squared minus bs plus cs minus c. And this is all after distributing the bs and the c. And so Now, I'm going to go ahead and pull together what I can. The 1/13 s squared and the b s squared are going to be able to come together because they're both with s squared. Now notice on the left hand side it's just 2s. So the coefficient with s squared on the left side is 0 because there is no s squared. So I'm going to set 1/13 plus b equals equal to 0. So b is equal to negative 1/13. Now I can combine the parts with c, which is cs and bs. So cs minus bs equals 2s. And then I can solve that way. Or I can go ahead and take just the constants, which is 22s over 13 minus c. So 2s over 13 minus c equals 0. And then I can solve that is 25. So 25 over 13 minus c equals 0. So add c, so c is equal to 25 over 13. So now that I have my a, my b, and my c, once you get your a, b, and c, it becomes much easier. So a 1/13 times 1 over s minus 1 minus, or b, which is negative 1 over 13, times s over s squared plus 25, plus c, which is 5 over 13 times 5 s squared plus 25. Again, if you notice, our c was 25 over 13, but here we weren't going to have an s, so we needed a k. So we were going to need to somehow get a 5 up here because k is 5 in this instance. So what we did was we broke up 25 over 13 to just 5 over 13 times 5. And so we get that without making it look a lot nicer. And so we get 1/13 times 1 over s minus 1, or when we do the inverse, we got to do the inverse of both. The left side is just going to be y of t. And so the right side is going to be 1/13 times the inverse of s minus 1 is just e to the t because alpha is 1, minus 1 over 13th, s over s squared plus 25. If it's s on top, it's cosine, so cosine of 5t, plus 5 over 13. Our k is on top, so sine of 5t. And that's it for example 7. And so here you see how the Laplace transform is used to solve for a differential equation. And notice that it has to be of exponential order, which we talked about in the first set of notes.